If you remember, at the beginning of the quarter, we started talking about motion. And the entire quarter, all we've been talking about is how things move. Characteristics of moving bodies, how fast they're going, how quickly they're accelerating, how much momentum and force they have when they hit something else. And today I'm going to introduce a new concept to you, which is called work. Now, I'm not talking about the assignments and things that you already do from a day-to-day basis. What I'm actually talking about is how we calculate energy using force and distance, but we'll get into that in just a moment. I wanted to go on ahead and go through a quick review of all the quarter two concepts that we've covered, because they're all kind of important to understanding work. So we started off the quarter with speed and velocity. So what is speed? Speed is just how far you went and how long it took you to do it. So it's your distance divided by your time. Now, if we want it to be velocity, we just need to add a direction. So instead of saying I'm going 50 miles an hour, I would just say I'm going 50 miles an hour north. Or I'm going 50 miles an hour towards Bonner Springs High School. It gives me a direction, so now it's velocity. We generally don't use the term speed in physics or in science. We generally always say velocity because we assume there's a direction there. Common units for velocity are things like miles per hour. That's what our cars are all based on, right? But if you go anywhere else on planet Earth, you're going to see things in kilometers per hour. That's because everyone else uses the metric system, and that's what science uses. Now, for physics problems, most of the time, we use meters per second. And generally, whenever we're talking about an object moving at a high rate of speed, we're talking about how many meters for every second that it travels. So what's an example of velocity? Well, if you're traveling at 60 miles per hour, you are going 1 mile for every minute of time. Or you're going 60 miles every hour of time. That's your velocity. So what that means is if I travel at 60 miles an hour for an hour, I've traveled 60 miles. If I travel that same speed, but I do it for 2 hours, well, now I've gone 120 miles. So really, again, it's just how far you went and how long it took you to get there. Now, with speed comes another concept called acceleration. We all know what acceleration is, we've just never actually had to define it before. But acceleration is just a change in speed or direction. If I am sitting still, and I go from sitting still to moving at 10 miles an hour, well, I have accelerated up to that point. I didn't just immediately start going 10 miles per hour or 10 meters per second. I had to get up to that speed. And getting up to that speed, that change, is called acceleration. If I were to be going north and then got hit by an object and started heading west, well, then I would have accelerated. I changed my overall direction. So, what are the units for acceleration? Well, we generally speak of acceleration in meters per second squared, or meters per second per second. Basically, we're taking the speed, meters per second, and we're dividing it one more time by seconds. And that gives you meters per second, or meters per second squared. We can do the same thing for miles per hour if we're talking about an acceleration rate per second. What do I mean by that? Well, I could say you are accelerating at 1 mile per hour per second. And what that means is every second you're increasing your speed by 1 mile per hour. So if I start off going 60 miles per hour and I accelerate at that 1 mile per hour per second rate, by the end of 2 seconds, I'm now going 62 miles an hour. It's fairly straightforward. In the example on the screen, you can see that the white truck and the blue truck are both accelerating, but the blue truck is accelerating at a more rapid rate. And this is why Tyreek Hill is so much faster, seemingly, than everyone else on the football field. It's not just because he has a high top speed. It's because he can get to his top speed very quickly. So he can accelerate at a faster rate than most players. Now, once we have the concept of velocity and acceleration, we moved on to talking about momentum. And what is momentum? Well, in layman's terms, it's how much oomph something has when it collides with something else. And it's simply calculated by taking the mass of something and multiplying it by the velocity. It's really, really, really straightforward. And when we start looking at that equation, we can pick out some relationships between the different variables. For instance, if I keep my velocity the same, but I change my mass, by however much I change my mass, that's how much more momentum I'll have. Or if I keep my mass the same, but I increase my velocity, well, whatever I increase my velocity by is how much more momentum I'm going to have. I'll give you an example. If I take a ball that weighs 1 pound and I throw it at 50 miles an hour at your head, or I take a 2-pound ball and I throw it at the exact same velocity, 50 miles an hour, the one that weighed twice as much is going to hit with twice as amount of momentum. And we know that because heavy objects hurt a lot more than small objects. Once we kind of have an idea of what momentum is, well, then we can move into force. And just like with speed and acceleration, or velocity and acceleration, momentum and force share the same relationship. What I mean by that is acceleration is the change in speed over a certain amount of time. Well, with force, force is the change of momentum over time. And it's that simple. And we calculate it by taking the mass and multiplying it by the acceleration, the amount that the object is accelerating based on how hard it's pushed. Because a force is just a push or a pull. So depending on how hard I push you, I'm going to change your acceleration at a different rate. Here's what I mean. If I'm running at you at 10 miles an hour and you're sitting still, when I hit you, I'm going to be pushing against you and I'm going to move your mass and accelerate your mass at a certain rate. If I weigh twice as much, I'm going to apply twice the amount of force when I hit you, and you're probably going to go careening off in the other direction twice as fast. So force is describing how much we change momentum. Thankfully, there was a really cool dude who figured out all of this stuff for us hundreds of years ago. His name was Sir Isaac Newton. And Sir Isaac Newton came up with 3 laws. 3 laws that really governed moving bodies and force. His 3 laws were as such. Objects at rest tend to stay at rest, and objects in motion tend to stay in motion unless acted upon by an outside force. Again, that just means if you're sitting still, you're not going to move unless something pushes or pulls on you. If you're moving in a certain direction, you'll continue to move in that direction until something applies a force to you. Slow you down, change your direction, change your speed. Maybe they come and hit you in the butt and you go faster. Well, that hit in the rear end was a force applied to you. Newton's second law is force is equal to the change in momentum over time, or F equals ma. And his third law was that for every action there is an opposite and equal reaction. Another example of this is the leaves here on the trampoline. What you see is as the person falls onto the trampoline, the bottom of the trampoline gives out, and those leaves stay suspended for a little while. Now, the reason the leaves don't fall initially is because that trampoline is there keeping them from falling. It's actually pushing against the leaves, while the leaves are pushing down against it. So what you have there are 2 forces operating on each other, and since they're not moving, the forces are equal. So the leaves are pushing down just as hard as the trampoline is up. Opposite equal reaction, right? And you'll notice that there's no motion. Objects at rest stay at rest. But as soon as that trampoline is moved because the person falls on it, well, now that force is no longer pushing up on the leaves. And gravity is now the only force that is operating. So it falls. The leaves fall. If you look at Bart Simpson, he is sitting in a chair. The chair is not moving and he is not moving. As soon as he applies a force, which is shooting that gas out the end of the fire extinguisher there, That applies a force backwards because we're pushing out force forward. Think about this. We have gas in the container and we release the gas, and the gas comes out with a certain amount of force. Well, in order to do that, it had to push backwards at us, which is why Bart starts flying down the hallway when he releases that fire extinguisher. For every action, there is an opposite equal reaction. And Bart would not have moved unless a force was applied to him. Thus, an object at rest stays at rest unless operated on by an outside force. And we can calculate how fast Bart flies off in the other direction if we know how much he weighs and how much force was applied to him. Conversely, if we know how much he weighs and how quickly he accelerated, we can calculate with how much force was applied to him when he turned the fire extinguisher on. Now, one of the things that I wanted to make sure I addressed before I moved on was talking about force and gravity. People tend to get a little bit confused when we're talking about gravity. Because force is equal to mass times acceleration, and the Earth is always pulling at you essentially with an equal amount of force, all objects will accelerate downwards due to gravity at the exact same rate. So a feather, which weighs a hundredth of what, say, a bowling ball weighs, both of them will fall to the ground at the exact same rate. Why is this? Well, because a feather has less mass, and because it has less mass, there's less gravity operating on it. Well, because there's less gravity operating on it, it's not being pulled as hard as far down. However, it also doesn't weigh that much, so it doesn't take that much force to begin with to move it. The bowling ball has much more mass, and thus there's much more gravity pulling on it. But because it's more massive, it requires more force to move. And believe it or not, because of this relationship, this directly proportional relationship, both objects will fall at the same rate. Because even though the feather weighs less and has less force being pulled on it, it doesn't take as much force to move it the same speed. And the same thing is true for the bowling ball. Even though it's much more massive and it's having more force, more gravity pulling on it, well, it takes more force to move at that same speed. Thus, they always fall at the same rate. And the only reason why we see feathers fall more slowly, or a piece of paper fall more slowly than objects, like a bowling ball here on Earth, is due to wind resistance. Because those objects are so light, the air actually applies a force upwards and slows it down. But because a baseball or a bowling ball have more mass, they can overcome that weak force of air resistance, and basically the air resistance doesn't even really apply to it at all. So then it just falls like it should. The bowling ball and the feather there are in a room with no air. And if they're in a room with no air, well, then they'll fall at the same rate because there's no air resistance acting on them. There you go. Fun stuff, right? Okay, so this gets us into work. What is work? Well, work is just a measurement of how much energy is expended when applying a force to move an object. Let me put it in simple terms. We're just trying to figure out how much energy it takes something to move it. You're taking force and you're multiplying it by distance. That's it. That's how you calculate work. So, for instance, if I'm moving a car 10 feet, and then I move that same car 20 feet, it took twice the amount of energy to move it 20 feet, because it went twice the distance. It's that simple. It's actually a fairly easy thing to calculate. What are the units that we use for work? Well, like with speed, which is like meters per second, or with acceleration, which is meters per second squared, or momentum, which is kilograms per meters per second, or force, which is kilograms per meters per second squared, well, once you get into work, as you notice, we're kind of combining these units together. Work is represented by a unit called a joule, which is 1 kilogram per meter squared per second squared. Let's use some examples. It makes it a little bit easier to understand. So, for instance, if we have a van and a kid in a toy car, the mass is much different between the van and the toy car. The van weighs much, much more than the toy car does. Thus, if we are going to move them the exact same distance, say 10 feet, it will take much less energy to move the boy. And it requires much less force to move the boy, right? I don't have to push as hard, right? The harder I push, the more force I give it. So if I'm not pushing the boy as hard as I'm pushing the van, well, then I'm going to use less energy. It's fairly straightforward, right? And the same thing is true if I take that same van and it takes a certain amount of force to move it. Well, if I move it 10 feet and then I move it 20 feet, it took twice the amount of energy or work to move it 20 feet than it did 10 feet. It's a directly proportional relationship. So some of you are probably worried right now thinking, oh great, we have more calculations to do. I just want to get to Christmas break. Don't worry. I'm simply bringing this up as a concept because when we get back from break, we're going to talk about work and how to make ourselves or how to allow ourselves to do less work by using things called simple machines. Things like levers and pulleys and ramps, which make our life much easier. There's a reason why you don't hold a hammer high up on the handle. You hold it down low. Because, well, you use the lever to allow you to do less work to hit with more force. And we'll get into all of those types of calculations and relationships when we get back. So, all you need to know about work right now is it's a directly proportional relationship between the amount of force you apply and for how long or what distance you apply that force for. And it just describes how much energy is needed to do that. That's all work is. Don't worry, we'll get into it when we get back. I hope this video was useful for you, and well, have a great break. Take a load off. If you don't have to do anything, don't do anything. Relax, play some video games, watch some Netflix, whatever you want to do. When we get back, we're going to be learning about simple machines and how to help ourselves do less work. That's all I got for you. Merry Christmas. Happy holidays, Happy New Year, Happy Kwanzaa, Happy Hanukkah, all of the different holidays that are occurring between now and the time we get back, happy that. See you later, Braves.